I'm going to summarize the types of nuclear decay in this table and list the particle that's involved, whether that particle is produced during the reaction or if it's part of the reaction. Also, the effect on the nucleus when the reaction occurs, and I'll also be providing an example of each type of nuclear decay with a balanced equation, and then discuss when that process is likely to occur. So this really has to do with the belt of stability that we spoke of in an earlier slide. So I'm going to start out with excuse me, alpha decay. So if I put a 1 there, alpha, remember the alpha particle could either be written with the symbol alpha or helium nucleus, but alpha decay, we may refer to the process as that, or alpha emission. So since an alpha particle is emitted, either one of these terms would be referring to the same thing. So the alpha particle, I've written over there, the mass is 4 and the charge is 2 because it's 2 protons and 2 neutrons. And again, we may see that written as a helium nucleus because the nucleus of helium has 2 protons, so its charge is 2, and 2 neutrons, and the charge is, or the mass is 4. What happens inside the nucleus is the atomic number decreases by 2. So the atomic number decreases by 2 because if the nucleus gets rid of 2 protons, then that nucleus becomes the element 2 atoms lighter than it started. And an example that I'm going to use is uranium-238. And uranium is element number 92. So it's nice to have a periodic table handy. So uranium is atom number 92. That's how many protons it has in the nucleus. And so that is the charge. And this is unstable because the nucleus is too big. So this would undergo alpha emission or alpha decay. So if we were told that uranium-238 decays by alpha emission, we would know to write the alpha particle on the product side. So that is a particle that's created and emitted. And now, since our equation has to balance, we can figure out what the nuclei is. So 92 is the sum of the charges. So an alpha particle has a charge of +2, so we know that we have to have a 90 right here. And then we can look at the periodic table to see what element that would be. So when uranium undergoes alpha emission, it turns into a thorium nucleus. Thorium is atom number 90. So that is thorium. And then which particular isotope of thorium is created depends on the nucleus that underwent the decay. So we just have to figure out what number plus 4 adds up to 238. So that is 234. So uranium-238, its nucleus basically spits out an alpha particle, and what's left is thorium-234. When this is likely to occur, I'm just going to write all nuclei that are greater than element number 83, which is bismuth, undergo alpha emission. So there is some point where the nucleus is just too heavy. So everything past bismuth is going to decay by alpha emission, or I remember it because polonium is Madame Curie's country, Poland, so that was named after her. So polonium and beyond, all of those isotopes would undergo alpha decay. So let me put a line across here. The next type of emission we're going to discuss is beta emission. And remember, a beta particle is an electron. So I'm going to write that weighs 0, has a charge of -1. I should be writing that in the particle side, but beta emission, actually if we saw that we might not see the charges. Beta decay, or we might see it written out, beta emission. So this is when a nucleus emits a beta particle. So that particle, beta, has a mass of 0, a charge of -1. And since that's exactly what an electron has, we could also write the symbol for an electron. So mass of 0, charge of -1. And we know that an electron does have mass, but it's negligible mass, and so we can write 0 for that. And what happens inside the nucleus there, which I find this to be the oddest type of decay, is that the atomic number increases by 1. So the atomic number increases by 1. And what's really happening inside the nucleus is a neutron turns into a proton. So if somebody would have told me that could occur when I first started chemistry, I'd say, no, sir, that can't happen. But a neutron will turn into a proton. So if we write the, oh, I've got that. No, that's right. The charge is on the bottom. The mass is on the top. So a proton has a charge of +1. It also weighs 1. So proton weighs 1 atomic mass unit, so does a neutron. And the electron is not an orbiting electron. It's an electron that is created during this process. So again, any equation that we write, the charges across the bottom have to add up on both sides and be equal. So +1 and -1 equals 0. 1 plus 0 equals 1. And so when a proton, if we think about it, when a neutron turns into a proton, then that nucleus has 1 extra proton. So that's why the atomic number increases by 1. And a common example of that is carbon-14. So if we write the symbol for carbon-14, its mass number is 14, the charge is 6, and if we remember the difference of the mass number and the atomic number, that isotope of carbon has 8 neutrons. So that's unstable because up to element number 20, calcium, a stable nucleus likes to have equal numbers of protons and neutrons. So this isotope has too many neutrons, so this will decay. And I'm going to put the beta particle first. So again, we need to get used to the fact that we might see the particle written as an electron or the symbol beta. So if we're told on a test, for example, that carbon-14 decays by beta emission, we would write the beta particle on the product side. That's very important. And then to figure out the nucleus that's missing, we just have to do the math. So carbon 14, this always confuses me, but what number minus 1 gives us 6? That's really the best way to think of it. Not 6 minus 1, but what number minus 1 equals 6? So that would be number 7. And then to figure out what atom that is, or what nucleus that is, we just look at the periodic table. So when carbon 14 undergoes beta emission, an atom of carbon becomes an atom of nitrogen. And then the symbol would, mass number would still be 14. So this is probably strange to me because carbon's a solid and nitrogen's a gas. So that's the one that just seems kind of crazy. And this would occur if we think back to what an isotope symbol means, having 8 neutrons in the nucleus and only 6 protons in the nucleus. That means that there's too many neutrons, but the way the book would state that would be the neutron to proton ratio is too high. Again, that just means too many neutrons. Or if we're thinking about the belt of stability, which I might try to draw, I guess I've got room here. So our belt of stability goes a slope of 1 up to atom number 20, calcium, and then the slope increases. So we could say that this isotope, where this is neutrons, the x-axis is protons. Another way of stating the neutron to proton ratio is too high is stating that this isotope is above the belt of stability. So this is really like simple algebra when you're learning graphing. So this stands for the y-axis, the neutrons. So too many neutrons means we're above this belt of stability. Protons will always be the x-axis. All right, the next type of decay I'm going to talk about is positron emission. And a positron, remember, is a positive electron. So that kind of sounds like an oxymoron, because we are taught that electrons are negative, which they are. But positron emission, positron, the particle there we write as an electron with a charge of +1 and a -0. So in this case, we wouldn't write a beta symbol with a +1 because a beta particle means that that particle has a charge of -1. So it's probably more technically correct to write a beta particle as the Greek symbol beta instead of writing it as the electron. But since it's the same thing, we write those two symbols interchangeably. So a positron, the symbol is just an electron with a charge of +1 and a mass of 0. So what happens, or the effect in the nucleus, is the exact opposite of beta decay. In this case, a proton turns into a neutron. So if we write the particle with the charge across the bottom and the mass on the top, a neutron has no charge, its mass is 1. So to balance this equation, we'd have to put a 0 here, because 0 plus 1 in the product side equals 1 on the reactant side. And then 0 plus 1 equals 1. So the particle emitted, this is our positron. And trying to get the shadow off of here. An example of that, of positron emission, I'm going to use chromium-50. So we might just be given the symbol or the word chromium-50. So we're going to have to get out the periodic table, unless we have it memorized, and see what atomic number chromium has. So chromium is element number 24, which means it has 24 protons in the nucleus. So we know that the charge of that nucleus is 24. And again, we're talking about spontaneous reactions. So the reactants side will simply have the isotope that's unstable. So chromium-50 is the only reactant. If we know that decays by positron emission, I might go ahead and put the positron first and then figure out what the resulting nucleus is. And again, it's just doing the math. What number plus 1 equals 24? So that would be 23. And that's the charge of the nucleus, but that also is the atomic number. So the atom right before chromium on the periodic table is vanadium, and the mass number in this case would not change. So since a positron has no mass, then, and the masses across the top have to add up, just as the charges across the bottom have to add up, you would see that chromium would actually, a nucleus of chromium would turn into the nucleus of vanadium, because vanadium is atom number 23. Okay. This is likely to occur when the neutron to proton ratio is too low, or there's too many protons in this instance. So if a proton turns into a neutron inside the nucleus, that's because there's too many protons. Otherwise, that reaction would not occur. So we also might see that written as, oops, that's a little bit too steep of a slope for the belt of stability, but that would be below the belt of stability, so the number of protons here, in this case, 24. And so if that atom is below the belt of stability, that's when positron emission is likely to occur. The next nuclear process we're going to talk about is electron capture. So I don't think I'm going to, well, I guess I'll call that number 4. But in this case, the electron that's captured is actually an orbiting electron, so just a normal electron like we think about, instead of the electron that's actually created during a nuclear process. So electron capture is going to have the same effect in the nucleus. So let me just write that down. Electron capture. So the particle is an electron, mass of 0, charge of -1. And the overall effect is still the same, that a proton turns into a neutron. But in this case, we're going to write the proton as a reactant, and the electron is part of that reaction. So it's, I think of this like the old Pac-Man, where the little creature gobbles up the dots. So the nucleus actually grabs an orbiting electron. So maybe I'll write that there. So the electron would be written on the reactant side because it is part of that reaction. So this is where a proton and an electron combine to make the neutron. So charge of 0, mass of 1. So I should have written the effect, so I'll do that right in the middle. The atomic number decreases by 1. So that's going to occur for both of these cases. So I guess I'm glad I forgot to write that across the top. So the effect is the same for both of these types of nuclear decay. The example I'm going to use for this is selenium-72. So if we're given just the symbol selenium-72, we've got to figure out what the charge is, or what the atomic number is. So selenium is element number 34. So that has 34 protons in the nucleus. And if we're told that selenium undergoes decay by electron capture, the selenium has to actually grab an electron, the nucleus. So it grabs an orbiting electron. So the electron's written on the reactant side. And so now, for me, the math is a little easier. 34 minus 1, because this is the reactants, that's going to equal 33. And then 72 plus 0 means our mass number stays the same. And then we get out the periodic table and look to see what atom number 33 is. It's kind of hard to see here. So we would write AS. Astatine, that's kind of hard for me to say. Okay. So this also occurs when the neutron to proton ratio is too low. And what the distinction is between when is the positron emission going to occur, or is electron capture going to occur? Electron capture is more likely to occur for heavier nuclei. And not meaning heavy as in past polonium. Anything past polonium is going to undergo alpha emission. But some of the lighter isotopes, if there are too many protons in the nucleus, then if we think about selenium versus chromium, selenium's nucleus has a greater charge than chromium. So the greater the charge in the nucleus, that means the more positive it is. So the more positive the nucleus is, the more likely it could actually attract an orbiting electron into that nucleus. So it sort of lures the electron toward it. And what I did not write next to each one of these, now that I'm out of room, I'm really done with the table, but I should have also written that each, or I'll write it here, all reactions also emit gamma radiation. So that's what makes the nuclear decay so dangerous. So remember, a gamma particle has a charge of 0 and a mass of 0. So if I wrote plus gamma here, that would be correct. Plus gamma here, and plus gamma, and again plus gamma. It's kind of like in algebra. We don't have to add 0 to the equation because it doesn't change its numerical equivalence. But this is that highest energy radiation, and all nuclear processes are highly exothermic. So each spontaneous reaction, each spontaneous nuclear reaction is highly exothermic. So that means it gives off a lot of heat energy. So highly exothermic, and the reaction is the system. We are the surroundings. So the energy that's given off by the equation, the system, is going to go into the surroundings. So if we're around, we would absorb that energy given off, which makes nuclear energy very dangerous for our biological molecules in the body.